Hi, everyone. My name is Ovais. I work in the infrastructure team at Snap, where I oversee a bunch of teams, including our caching and storage platform teams. At Snap, like as Khwaja mentioned, we have caches. Our cache fleet is powering hundreds of millions of QPS. We are very passionate about improving the performance as well as reliability of all those caches. So much so that we ended up acquiring a company that was solely focused on optimizing Redis. Most of you know about that, KeyDB. KeyDB is a fork of Redis 6.2 with a truly impressive set of features, including a lot of performance and a lot of operational reliability features. I'll talk through our journey of how we went from other engines to KeyDB, how KeyDB worked so well for us for so long, the learnings we got of operating such a big fleet, both in terms of cost, latency, throughput, performance. We will also talk a little bit about the overhead of running a fork implementation for so long outside of the main community. Lastly, we'll talk a little bit about our Valkey journey, how we evaluated Valkey, how we thought about it, what went really well in that migration process, what didn't go according to the plan. And essentially, like if we have to do it all over again, what we will do differently. The goal is that you walk away with some practical techniques that you can apply to your stack, be it powering like millions of QPS or hundreds of millions of QPS. Well, let's see. Perfect. So we'll talk a little bit about how Snap evaluated Valkey. We'll talk a little bit about our caching and our architecture of our cache, of our storage and caching platforms, essentially. We'll talk about the challenges that we saw with integrations, how the integration went. We will talk about learnings and next steps. So as Madeline mentioned, prior to about 2 years back, all of Snap was running on KeyDB. KeyDB is like a fork of Redis 6.2, as I was mentioning. It has a lot of performance features. For example, it has multi-threading, which is different than IO threading. It was but then it was able to do a lot of QPS out of it. It had its own fast sync and forkless PG sync, which makes those syncs faster and faster. It had its own AZ affinity features where the reads would go to the same zone. Then that was super important to reduce our costs across AZ Trust. So came Valkey. The biggest thing that drew us to Valkey was its open governance model. Essentially, we were having a lot of issues with getting Madeline talked all about the issues that most people were having getting their features in Redis, and KeyDB was no different. We basically also look at the roadmap of Valkey and features like IO threading, which was already being worked on by the time we started looking at it. Features like dual channel replication, they all were super great features, and we wanted to go utilize them, as well as we saw that there's a lot of potential in the Valkey space in terms of future performance improvements, and that was the other part of it. Alongside, as I was mentioning, running a long-lived fork comes with its own issues. We were not able to easily move to Redis 7.2, for example, by that time. So that was another issue. So we wanted to get rid of our fork implementation and get to the main line. Okay, with that, let's talk a little bit about, one second. Guys, and Mike, I need a little bit of help here. It's not in sync. Cool. So let's talk a little bit about our storage abstractions, which are super important. Which were super important in a lot of this migration, as well as in the past, in other things. So essentially, like the high-level TLDR is that applications don't talk directly to the storage engine or the caching engine. So there is a storage abstraction down up there, and there's a REST proxy that we are running. This allows all the application developers to be able to utilize the APIs as is, while it also allows all the infra developers to keep on changing the backends. For example, in this case, we switched from KeyDB to Valkey in the backend without any of the application developers knowing about it. Yeah, so let's talk about the REST proxy in particular. I don't think I'm not gonna repeat everything that Khwaja already said about REST proxies. The only thing that I'll add is that we also utilize it to handle large clusters. So we have a lot of clusters where 400 nodes are not enough. So what we end up doing is clearing cluster groups, meaning there are a bunch of clusters. And the REST proxy allows us to move from one cluster to multiple clusters. So one cluster to two cluster groups, or from two cluster groups to 8 cluster groups. Maybe I'll talk a little bit about actually, let's see if I can go back. Okay, that's okay. So one downside of the REST proxy is basically what we were talking about in the previous slides, which is basically around head-of-line blocking. So that's a basic issue with REST proxies in general. Essentially, one slow command is going to cause huge issue. The way we mitigated it is by creating a lot more connections. The other issue that we saw with REST proxies was around huge mgets, where we are talking about where one shard is down. In which case, what we ended up doing is basically we created a custom mget command that is basically allows you to do partial failures. So those are the two major things that we have in our proxy layer that helps do a lot of heavy lifting. So this slide is talking a little bit about how Snap hosts the caches. So almost all of the caching workloads, Redis or non-Redis, is hosted in Kubernetes for us. We basically have an operator that basically manages the life cycle of the cluster, like when you're trying to upgrade, when you're trying to scale out, scale in, change the machine type, everything, the operator handles that. And the control plane is mainly responsible for handling the provisioning aspects of it or the monitoring aspect of it. In order to utilize Valkey, it has to fit into this pattern. And yeah, with that context, let's talk about how we integrated Valkey in our stack. So based on the last diagram, you can totally imagine like it's not so straightforward to just do a binary swap. So what we ended up, for example, like the hosting stack assumed a lot of KeyDB features. It required, and I'll give you one example. So when you're trying to do an upgrade, you attach a new replica, you let it handle the traffic, you eventually want to remove an old replica. When time comes to remove the old replica, you want to remove it, but in our case, what we have seen, that all the clients will start timing out. So what we implemented in KeyDB was a functionality where we leave the replica there, it will keep returning moved to every single command, not time out, but will not be serving anything. And that's a functionality that Snap contributed to the open source Valkey as well. There are a lot of performance and cost related things that were in KeyDB that we needed in Valkey. For example, AZ affinity is the most important one. A lot of when traffic goes cloud in a lot of these cloud providers, it costs a lot of money. And that's the main thing that we are trying to save there. And there's definitely a bunch of unique features, but those are not going to be blockers. Like, for example, KeyDB has sub-key expiry, and at some point, like in the next quarter or two, we'll start tackling those workloads. So the first step, as I was mentioning, is zonal awareness. Like that was literally the first commit from Snap's perspective to Valkey. So we ended up it was very easy port as well. So we ended up upstreaming that change in the very beginning. The high-level reason is like it doesn't work in silo either. It works in really close collaboration with how our control plane and how our operator works. For example, like when we are trying to create a shard, we have to make sure like there is one replica of shard in each of the zones where the customer traffic is. The operator and the control plane have to ensure that. And once that is ensured, the proxy layer as well as this Valkey same zone routing functionality will be able to route rates to those replicas. We did a very detailed analysis of trying to figure out like what gaps there exist in Valkey versus what corresponding functionality exists in Valkey. For example, KeyDB had multi-threading, but Valkey has IO threading. So they definitely work differently. So we have to understand and benchmark all the how they all work well together or not, and if we'll get the same throughput or not. But leaving that aside, we have a list of all of those features that KeyDB had, and we picked and choose really carefully which ones to port versus which one to upstream. We picked 8.2 RC like sometime last year, like in January, I think we kicked off this project. That's when RC was almost there. We picked that build, ported all the features that we really needed. Traffic, router traffic, but somehow it all worked fine till we reached about like 9 or 10 kqps. At around that time, we saw that a bunch of crashes are happening in the system. So most of these projects don't go according to the plan, right? It's like this is where we had our first main hurdle. We ended up like creating a Helm chart, repro on one side. We were able to track it to the TLS offloading work that was new to 8.2. So we had some half a confidence that it won't repro in 8.02. So we were able to ensure that. We were also able, using the repro, one of our Valkey committers, Yuri, was able to fix it. However, like with that experience, what we ended up learning is that we, like none of the cloud providers were running 8.0.2 essentially. So a new release will need some baking period. So what even though we knew that we'll not be hitting production for a few months, but we still wanted to go back to 8.0.2. So that's what we picked as a baseline. So we reported all of the fixes that we needed to, move to 8.02 to run a bunch of benchmarks. And with that, the project moved into the actual prod rollout phase. And in terms of prod rollout, we were very we were very careful in trying to figure out which workloads to migrate. As I was mentioning, like Valkey has a lot of features around forking, memory management, a lot of features around IO threading. KeyDB also had some similar features. We wanted to make sure there's no regressions anywhere. So the most important thing is to make sure there's no regressions in throughput, no regression in performance, no regression in cost as we are migrating. We are not looking for a huge lift here with Valkey migration because we knew KeyDB had all of those features as well. So with that, we first picked the CPU-bound workloads, followed by high memory workloads, followed by really high write rate workloads. So those are the three divisions that we created up front. Apart from that, within each use case or workload type, what we picked is we started looking at the lowest tier to the highest tier, meaning the lowest critical workload. Even if it goes down, it's not going to cause a huge outage for Snap, versus the highest workload is the last one. So yeah, so this is a similar thing in a different variant. It's like CPU-bound workloads. The most important thing I would say there is that what we are looking there is to ensure that multi-threading done in KeyDB way gives you, and multi-threading gives done in Valkey way gives you the same throughput, at least. And ideally, we're looking for some improvements from Valkey. In the second one, we are trying to just make sure that dual-channel replication keeps on working. And the third one is basically a similar variant of it, but then we have to make sure that all the right knobs are in place. So after we do migration, we don't start getting a lot of pages. Within each cluster, the logic was very simple. We'll dual write. All of these are cache clusters, so we are talking about a TTL of 24 hours to max a week. So worst case, you have to dual write for a week, and now you basically, the other setting, the new cluster is ready. Okay, so let's talk about the first workload, so high CPU workload. We specifically picked it up because we didn't want to worry about memory pressure initially. We wanted to make sure that Valkey's I/O threads work the same way as KeyDB's the way KeyDB worked is that all of the threads were basically processing as well as doing I/O. They were also doing TLS termination and everything else. And now, we also wanted to make sure that our migration tooling is fully hands-off. So we don't have to keep worrying about migration because we are talking about hundreds of clusters here. And it's like going to be a pain if we have to keep doing that. So that was the other thing that we wanted to get out of it. The first set of benchmarks worked really well. Like we were trying to do single get requests, single key get requests. And in that case, actually, Valkey had a very good, we have a lot of test cases that we are going through, basic test cases like sending a bunch of requests via YCSB, seeing what the throughput is. We'll bring down replicas and see how the system behaves. We'll bring down primaries and see how the system behaves. We'll try to do an upgrade, see how the system behaves. In all of the cases, Valkey was at par, and actually when the replica is down, Valkey was much better actually in terms of throughput and performance. However, we also have use cases which are using the really, really large batches. And we're talking about batches of thousands of keys. The way mget command works, I think we have to go back a little bit into the slot aspects of Valkey or Redis. So the way mget command works, or any Valkey command works, is that you can only direct it towards a shard. Meaning that even if you have 1,000 batch requests of 1,000, and you have a cluster size of, say, 10 or 9 or something, each of those requests are divided between slots first. And then you are sending those requests to each slot. Meaning that we are, with 16,000 slots and 1,000 batch size, there's always going to be pretty much like a single request, get request that we are going to send. So we are seeing a lot of pressure in terms of command parsing on the Valkey side instead of command execution. KeyDB had a feature which was called cross-slot mget, which allowed you to send requests to the same node for all of the keys it hosted, irrespective of the slots. So that is the main feature we ported here, and we got back to the same baseline. We are still trying to work with the open source community on trying to get this feature in. There's an issue open. We potentially will get the same perf out of pipelined. So we have to re-benchmark everything after 9.0 is integrated into Snap's ecosystem, and then we'll restart that cross-slot discussion with the community. We also have a feature like in KeyDB, which is called like CPU throttling. The way that works is that it ensures that admin commands always are able to reach the cluster by throttling requests once the CPU utilization of a node has reached 95% or more. That is another feature that we ported, and with that we were able to migrate all of these workloads. So at its peak, we were sort of migrating like 30 or so caches a week, so because of the hands-off nature of the tooling. Next up was the high memory utilization workloads. At a high level, we were just trying to figure out a number where we are comfortable migrating, where the replication buffer gets full. As many of you know, the way when a replica goes down, the way replication happens is master first sends the snapshot at a very, very high level. Master sends a snapshot to the replica, and then master sends all the change logs to the replica. That process takes time. In some cases, it can take minutes, depending upon the networking condition of the network, as well as the load on the machines. We are basically just trying to figure out how much replication buffer we can fill for each workload. So for essentially for each workload, we'll try to figure out how much replication buffer it gets filled within a minute. And then based on that, we were able to pick 15 minutes as a number that the team was very, very comfortable with migrating. I'm not, how many of you are familiar with full sync loops, by the way? No. Yeah, perfect. So at a very, very high level, the idea there where I was mentioning about where the primary has to send the snapshot, take a snapshot and send it to the replica. If the replication buffer gets full during that period, you will sort of have to restart the full sync, and at some point you might get into so much traffic that the full sync loop never ends. And that is the primary thing that we are trying to prevent here. One of the features that the way we prevented it in KeyDB was via a number of features. The most important one was write throttling. Write throttling prevents writing, accepting any write command when the buffer is almost full. So that is one feature. Apart from that, we have a lot of other features that we already talked about. I'm going to try to go a little faster now. We benchmarked all of these clusters. We ended up picking up 15 minutes as a target to migrate. All of 15, we'll migrate every cluster that cannot fill replication buffer in 15 minutes. It was almost 3x more than what we can tackle. Okay. So the next workload was basically high write rate workload. High write rate workloads, like 100% write rate workloads maybe, like rate limiting, or fairly high write rate workload, like 75% write rate. We have got 75% write rate workloads as well in our ML space. What we did here was we realized that in the other difference between KeyDB and Valkey is that in dual channel replication, the Valkey's replication buffer is on the replica, while KeyDB's replication buffer was on the primary. So, and there's no copy on write overhead on the replica. So what we ended up doing is increasing the replica's buffer a lot more, and tweaked down or write throttling on the primary so that the primary replication buffer never gets that big. And with that combination, we were able to migrate all of those workloads. This is the state we are currently in, actually. So we are currently migrated about 70% to 80% of the workloads, and we are currently trying to migrate this type of workload. Post-migration, while we are doing all of these migrations, we are also trying to look ahead to how to consume Valkey 9.0. So the biggest thing that we have a lot of changes in our forked implementation of Valkey as well. And some of those changes are related to auth-z. So one of the biggest things we did was to move our auth-z code to a module. And that was very good. That is going to help us a lot with reducing the code in our fork. We also created an open, we also moved to Prometheus and created an open telemetry module, which if people are interested, we can look at open sourcing that. A few learnings here. So at a very, very high level, abstractions and proxies look like they are overheads. But at certain scale, they are sometimes also leverage. And which is what helped us do this migration. If we didn't have a proxy layer, if we didn't have the right abstractions in place, I don't think we would be ever able to be successful with with this migration. Forking an open source project and keeping that long-lived fork there helps in the short term. Definitely, as I've not shown any numbers here, but in short, Valkey's performance was almost at par with KeyDB's performance. It's just that we had that performance multiple years earlier. So fork definitely helps you with the speed, but at some point, it ends up causing you to not be able to consume the other good things that are happening in the community. And that's another learning that we have got. Yeah. And definitely the correctness and operational safeguards are very, very important for us. We cannot have cases where like a lot of our caches are causing issues, for example. The next step for Snap will continue pushing changes to upstream, continue pushing improvements in our Kubernetes operator. There is a thread to start working on an open source Kubernetes operator. We'll be happily involved in it. We can talk more about it and that issue. For Snap itself, we are also trying to move to Envoy proxy from our REST proxy. And that's more in terms of cost aspects of it, as we are reaching billions of QPS number, essentially. So at hundreds of millions of QPS number, the proxy overhead is okay, but then at that point, we are basically thinking to not only move our proxy logic to Envoy, we are also looking to move our business logic to Envoy, where we are basically rewriting our feature stores in Envoy, for example.